Hello, everyone, and welcome back to our DSA series. I'm so excited for today's session because we are moving beyond just making things work and into making things professional. Today, we're talking about in place array manipulation, which I like to call the art of no spare room. Imagine you are trying to reorganize a bookshelf, but here's the catch: you aren't allowed to put a single book on the floor. You can't clear a shelf to start over. You have to swap, slide, and rotate items within that tiny existing space. This is the essence of what we do as senior engineers when we strive for open space complexity. It's about being incredibly clever with the memory we already have. Before we dive into the mechanics, make sure to follow, like the video, and hit that notification bell so that you don't miss any upcoming topics in this series. For more deep dives into the interview prep, check out my channel CSAITTL. Let's get to work. So, why are we obsessing over O1? Why not just copy the array? In our diagram, look at the naive copying. It's like hiring a massive moving truck just to rearrange the furniture in the room. It's safe, but it's incredibly expensive. In a production environment, creating a full copy of your data can be a disaster. If you're processing gigabytes of server logs or manipulating high-res images on a mobile phone, that's extra allocation. That second moving truck can literally crash the system. O1 isn't just a fun math constraint, it's a survival requirement. We must solve the problem using only the memory we already have. It's riskier because you're overwriting your input, but it is the peak of efficiency. If you're looking for extra notes on these memory constraints, I have posted a deep dive document on the GitHub. You can find the link in the description below. To master the in place world, you need a master key. That key is the two pointer technique. Think of it like having two hands working on the same array simultaneously. Your first hand is the read pointer, that is your scout. It hunts through the mess of array looking for keepers, the elements you actually want to stay. The second hand is the write pointer. This marks the spot where the next valid item needs to land. Everything behind the write pointer is what we call a save or process space. Everything between the write and read pointer is effectively garbage or unknown. By moving these pointers at different speeds or based on different conditions, we can restructure the entire array without ever needing a temporary storage area. This is the fundamental mechanics behind almost every open space problem you'll ever see in an interview. Let's look at the practical application, removing elements. A junior mistake is to find an element, delete it, and shift everything else left. If you do that in a loop, you're doing an O n square work. It's painfully slow. Instead, use a packing a suitcase method. Look at the example. We want to remove all threes. A read pointer sees a 3, that's garbage. We ignore it and then don't move the right pointer yet. Next, the read pointer sees a 2, that's a keeper. We copy it to the right spot and advance the right pointer. At the end of the pass, all our good stuff is packed tightly at the front of the array. We don't care what's left at the end. We just return the new length. We have collected our valid elements in a single O and pass and left the garbage behind in the unused section of the array. No extra memory, no redundant shifting. We can use the same logic for deduplication, especially in sorted arrays. Because the array is sorted, we have a massive advantage. Duplicate always live right next to each other. We don't need to have a heavy hash set, which could cost ON space, to track what we have seen. Our writer A writer pointer effectively asks, is the item the read pointer just found different from the last one I packed? In code that just if nums read is not equal to nums write minus 1, if it is different, we write it and move forward. If an interviewer asks you to allow at most k copies, say allowing 2 of each number instead of 1, you just change your look back distance. You check nums write minus k. This simple adjustment allows you to handle complex constraints while maintaining that perfect open space complexity. It's a classic level 2 interview question that becomes easy once you visualize the pointers. Now let's talk about the shifting, because this is where most bugs are born. Shifting has a golden rule. Direction matters. If you are left shifting to close a gap, you slide elements safely to the left. You iterate from left to right, which is in the forward direction. This works because the spot you are moving to is already a garbage. But look at the right shift hazard. If you are making a space and you iterate forward, you will move A into B spot before you have moved B. You end up with a dominoes effect of overwriting your own data. To shift right safely, you must iterate from right to left, backward. You move the last element first to create a gap. Always remember, shift away from the direction of the iteration. If you get this wrong in an interview, your logic will start to crumble. For a visual animation of this domino hazard, check out my supplementary files on the GitHub linked in the description. Let's apply that to a common problem. Move zeros. The goal is to push all zeros to the end while keeping the non-zero elements in order. We treat the non-zero as our keepers. Our pointer tracks the end of the non-zero block at the front. As the read pointer finds a non-zero element, we have a choice. We could just overwrite, but then we'd have to fill the end with the zeros manually later. A better optimization is to swap. When we swap the non-zero elements with the element at the right pointer, the zeros naturally get pushed towards the back as the non-zero move forward. By the time read pointer hits the end, the array is perfectly partitioned. One pass, O(n) time, and O(1) space. This clean, efficient, and shows you understand the how to minimize operation. Now we get into a trickier one, array rotation. We want to move everything from the right by k spots. If we move 1, 2, 3, 4, 5 to the right by 2, it should become 4, 5, 1, 2, 3. Now, how do we do this in place? Creating a temp array uses O(n) space. In many interviews, that's considered cheating or at least a suboptimal answer. Rotating one by one, k times, is O(n) by k time. That's way too slow for the if the array is too large. Moving elements in a circle is tricky because as soon as you move one element, you displace another. It feels like you need a holding area for the displaced items, but we are not allowed to have anyone. How do we move everything without using extra memory or taking forever? This is where a bit of mathematical magic comes in. This is one of my favorite algorithms in computer science because it feels like magic, but it's actually just geometry. To rotate an array in O(1) space, we use a triple reversal. Let's say k is 2. So step 1 will be reverse the entire array. The whole world turned upside down. 1, 2, 3, 4, 5 becomes 5, 4, 3, 2, 1. Step 2 is reverse just the first k elements. 5, 4 becomes 4, 5. Now now step 3 will be reverse the remaining element. 3 to 1 becomes 1, 2, 3. Look at the result. 4, 5, 1, 2, 3. It's perfectly rotated. The mathematical property is AB script R is equal to BR AR. By reversing the whole and then the parts, we have moved the blocks to their correct positions. It is O(n) time because we touch each element twice, but O(n) space. It's an elegant solution that interviewers absolutely love to see. In-place manipulation it's not just about numbers. It's huge for string comparison. Imagine an array of characters like AA, BB, C, and so on. We want to compress it to A2, B2, and so on. We use our two-pointer count. The read pointer scans ahead to count the run of identical characters. Once it finds the end of the run, let's say it counted 12 C's, we have to write that results. The gotcha. If the count is a multi-digit number like 12, we can just write 12 into one slot. We have to write 1 and then 2 digit by digit because We only write the compressed version, which is always shorter than or equal to the original run. We are guaranteed never to overwrite data that the read pointer hasn't seen yet. We never store the whole string, only the current count, keeping it as open extra space. One of the most famous in-place problem is the Dutch national flag problem. Imagine you have zeros, ones, and twos all mixed up, and you need to start them in a single pass. Sorry, sort them in a single pass. We use three pointers: low, which is tracking the end of zeros; high, which is for tracking the start of twos; and mid, our scanner. If mid sees a zero, we swap it to the low section. If mid sees a 2, we swap it to the high section. Very crucial detail. When we swap with high, we don't advance the mid pointer. Why? Because we don't know what we have swapped in from the back. It could be a 0 that need to be moved again. This invariant zeros on the left, twos on the right, and chaos in the middle is a key to sorting categories in a single pass without any extra arrays. Here is some senior wisdom. The algorithm is actually the easy part. The edge cases are where you fail the interview or crash the production server. Always check your boundaries. Empty array. Does line equal 0 break your code? Single element. Does your pointer logic hold up when n is 1? Rotation is greater than length. If you rotate an array of length 5 by 12 spot, that's just a rotation of 2. Did you normalize with k%n? If not, your code will do 12 passes for no reason. Stability. Does the order of duplicates matter for your specific problem? A senior engineer doesn't just write the happy path. They build a fortress around the boundaries. I've included a checklist of these production killers in GitHub repository, linked below. Definitely give that a read before you move to your next interview. To wrap up, let's look at the in-place toolkit. If you master these four patterns, you can solve almost any open space problems. First, remove. Use two pointers, read, write. Pack the suitcases and ignore the rest. Shift. Direction matters. Iterate backwards to shift right. And find third, rotate. Remember the triple reversal trick. Partition. Use three pointers to sort categories in one pass. Treat the array as your workspace, not just a storage box. Comment below and let me know which of these patterns you find the trickiest or what topic you want to see next in your DSA series. Don't forget to check the description for the GitHub link with the practice problems and additional reading. Thanks for watching CSAITTL, and I'll see you in the next deep dive.